kiddos, welcome to part 2 of Conformers. Last video we talked about ethane and Newman projections and how to set them up. And remember, the idea is that we're going to take the fact that single bonds can sort of essentially be rotated around each other, and that gives us different positions, okay, for all of the atoms in the molecules to sort of relate to each other. Those different positions are called conformations. There are some conformations that are more energetically favorable than others. In ethane, remember, there were only essentially 2 possibilities because there was only one carbon-carbon single bond to rotate around, and everything was hydrogens, and so it was either the hydrogens were overlapping and eclipsed, or the hydrogens were as far apart as they could get from each other and staggered. And what we talked about was that the staggered conformation was sort of the most energetically favorable. So we're going to look at a slightly more complicated molecule here of butane. Okay, butane is obviously saturated alkane, 4 carbons. And what we're going to do for this is we're going to look straight down the 2 and 3 carbon in our butane, because by looking down the 2 and 3 carbon in the butane, it gives us something other than hydrogens for our substituents that we're looking at. In fact, what it gives us is that it gives us, we've got 2 hydrogens, so for the number 2 carbon, we've got 2 hydrogens and a methyl group. And then on the 3 carbon, we also have 2 hydrogens and a methyl group. And that's going to give us a more interesting and robust series of interactions that we can have there. So let me draw sort of an initial Newman projection for that. And again, remember what a Newman projection is that we're essentially looking straight down, okay, the 2 and the 3 carbon in our case. So if you picture it sort of looking like this, I'm looking straight down this carbon. So this is my front carbon, okay? So we got 2 hydrogens sticking up and a methyl group. That's what all this jazz down here is, a methyl group hanging down. The back carbon then, okay, let me hold it up here. The back carbon has 2 hydrogens sticking down and a methyl group sticking up. So let me draw that Newman projection, and then we'll talk about some other conformations of it, and then we'll talk about energy. All right, so again, this is what we look like. Okay, so front carbon, okay, front carbon here, 2 hydrogens going up, methyl group coming down. The back carbon, I've got 2 hydrogens going down and a methyl group coming up. Obviously, in that case, the methyl groups are sort of as far apart as they can get from each other, and that's going to give us our name for this particular conformation. This is what's called an anti-conformation, or we could call it an anti-staggered. An anti-staggered conformation means those 2 methyl groups are as far away from each other as they can get. One sort of sticking up in the air, one sort of sticking down that way. And if we were sort of looking at the carbon or looking at the molecule like our eyeballs were facing down here, that's what we would see. Methyl up here, 2 carbons in a chain, and then the hydrogens sort of sticking off at their angles. Remember, we're trying to keep that tetrahedrality there. So they're sticking out at those angles. That's what's going to look like that. That should remind you immediately of your staggered conformation from your ethane, which should sort of indicate to you that, hey, that's probably the most favorable energy scenario where things are as far apart from each other as possible. So let's look at another couple of conformations as well, because we're going to have a little bit more variety in our conformations in this case than we could have had before. Okay, so let's talk about some of our other conformations here for butane. You'll see that I've started to draw some, and I want to draw the rest of those diagrams sort of while you're watching so that you can see them. This is our anti. Remember that that's what we had to begin with. We're looking down our 2 and our 3 carbon, hydrogen sticking up, methyl group sticking down, other methyl group is on the opposite side of this. And so we're sort of in our optimal energy situation, and I'm going to draw the energy part in here in a minute. But you can sort of see we're probably at the lowest energy there. There's not a whole lot of torsional strain. Okay, well, I mean, there's some, but there's not a whole lot of torsional strain, and there's none of the additional sort of strain that we're going to see here in a minute. Okay, so what that represents is, if we go back to what you were thinking about in the last video, is sort of if we went back and said, okay, 60 degrees, 60 degrees, 60 degrees, right here, the methyl groups are 180 away from each other, okay, on complete opposite sides. So what if we went back 3 steps and they were not 180? What if they were 0 away from each other? Okay, this is 0 away from each other. That would be this model here. That model's name would be exactly what you think it is, because it's the same as it was when we talked about our ethane. That is an eclipsed. Eclipsed meaning that they're overlapping, right? That you can't really see the stuff on the back one because it's constrained by the stuff that's in the front one. And so that's going to be our eclipsed model. So definitely a lot of torsional strain. We've got torsional strain. If we look at our model, we've got torsional strain hydrogens overlapping here. That's torsional strain. We've got torsional strain down here as well. And additionally, in addition to the torsional strain, we also have a new kind of strain here, because if you look at this, if I turn this up and you can see this, I can actually like turn my model so that things are like actually hitting each other. Okay, they're actually in each other's way. They're spatially constrained. And so that's going to give us a new kind of strain called steric strain. Okay, and steric strain means essentially that they're spatially, they're in each other's way. They're trying to occupy the same space, and that's not going to be a very favorable conformation. I've got essentially too many atoms in too little space. If this was a bigger gap between them, then yeah, I could have these turned up and it would be no problem if I had another couple of carbons in there and they were more spread out. But they're not. I mean, everything is pretty close to one another. Now you'll notice that, yeah, I could do some shifting on these as well. We're not going to worry about the multiple single bond shifts right now. We're just going to worry about one at a time. But they're sterically constrained. They're essentially in each other's way. That's a little different than the torsional strain that had a little bit more to do with the bonding, anti-bonding orbital overlap there, or the bonding molecular orbital overlap, more to the point for torsional strain. Okay, so that's full on eclipsed. So what say then, we'll go back to our energy model. Let me draw the energy model in here. So really high energy, okay, lower energy, somewhat high energy, and then lowest energy, if we sort of drew through there. Okay, obviously anti is going to be our lowest, full on eclipsed where these methyl groups are in each other's way. That is like the worst scenario. That's the highest energy scenario, so that's the least likely one. So what if we then said, okay, so I'm starting here at my 0, and then I'm going to twist 60 degrees. Okay? So if I twist 60 degrees then what happens is that my methyl group now is over here. So I've got my CH3 over here, and then I've got a hydrogen up here and a hydrogen over here. Now, what's going on in this situation is that they're not having as much torsional strain, okay? In other words, they're not overlapping each other. If we look directly along the bond angle there, there's not quite as much overlap. You'll see that hydrogen's in between these two. This one's out to the side here, so it's not in the way. And then the methyl groups, torsionally speaking, much more alleviated. They're not directly behind each other, directly overlapping. But you'll still notice that like there's kind of like still like a real like spatial consideration there. So we're still having a fair amount of steric strain here. And that's what's going to keep this model from being quite as favorable as this model, where they're completely as far away from each other as they can get. This model actually also has its own name, and it's a French word, and that word is gauche. Okay? So the gauche model means that the dihedral angle between our two biggest groups there, which are our methyl groups in this case, is 60 degrees. We made one 60-degree rotation. We were at eclipse where it was 0. We rotated once. We rotated the back one once 60 degrees, and that's a gauche conformation. Okay? Still not terribly favorable, but more favorable than the eclipsed. So what happens if we rotate it again then? Okay, so we're at gauche conformation. I'm going to rotate it again. If I rotate it again, then here is my new situation, Newman projection-wise. So now I've got my methyl group is up here, and I've got my hydrogens. Okay? So what that means then is that now I'm back to having a lot of torsional strain. My steric strain isn't as bad. Okay, if we look at what's going on here, my steric strain isn't as bad because the methyl isn't getting in the way of the hydrogen. This methyl is not getting in the way of this hydrogen. But we still have all of that torsional strain that we get from the overlap there of those bonding molecular orbitals. So still really high energy, a lot of torsional strain there from that overlap. Okay, so we rotate it again another 60 degrees. Okay, and that's when we get back to our anti-conformation where the methyls are as far apart from each other as possible. Okay? And so that obviously is going to be our most favored energy state. If we drew this graph-wise, and I didn't make this a separate graph, okay, but if we drew this graph-wise and said dihedral angle and energy, this is how this is going to go. eclipsed with the methyl groups overlapping each other. Very unfavorable, really high energy situation. We shifted a little bit, so we've relieved the torsional strain, but we still have a little bit of steric strain. More favorable, but still a little bit not our lowest energy situation. Twisted again, another 60-degree dihedral angle, and then that gets us up to, well, again, now we're overlapping, got a lot of torsional strain, not as much steric strain, but a lot of torsional strain. And then anti, we don't have really either the torsional or the steric strain, and so that's going to be our lowest energy consideration. So remember, you've got two types of strain that we're worried about here, and we're going to talk about cycloalkanes and eventually get to our chair conformations for cyclohexane here pretty soon. And we're going to add in a third type of strain, which is angle strain. Before us so far, we've got torsional strain that is from the molecular orbitals overlapping when we look at a Newman projection, and they're essentially eclipsed right behind each other. And then we've got steric strain where they're spatially actually sort of bumping into each other. That's steric strain, and that's a bad situation. By the way, this particular one doesn't have a special name. This is just another form of eclipsed, okay? It's not the worst eclipse. This is the highest energy eclipse because we've got the two biggest groups overlapping each other. It's obviously more favorable to be in this case than it is in this one because at least our steric strain is lowered here, but it's still causing some problems. And one of the reasons why conformers are so important to us, and they're really important medicinally and all of those important things to us, but as far as understanding organic chemistry, why conformations and conformers are so important is because it really gets you to think about what is the most energetically favorable positioning of my molecules. And it really helps you to start to think a little bit in 3 dimensions. And I highly recommend that when you start out that you're definitely using a model kit and sort of twisting it around and looking at it. But remember that when you get to actually solving problems like this, or when you get to your college level classes in this, you're going to be essentially working from paper and having to figure out things from there. So you definitely want to make sure that you're practicing taking a regular drawing of a butane and putting it into the proper Newman positions, and then figuring out what are the conformers from that Newman projection. All right, thanks a lot, kiddos.